This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, we are discussing the topic of hydrodynamic and thermal boundary layer in heat and mass transfer subject. Here, hydrodynamic boundary layer. Here, it is the simplest figure which is showing a stationary plate is kept in a fluid which is flowing with a velocity of u as shown in figure. The fluid particle which touches the surface of the plate, the velocity of this particle is reduced to 0 due to the viscous forces present between the fluid particle as well as the surface of the plate. That means at the intersection of the interface of the fluid layer which is touching the plate, here it is 0 now. So as we proceed in just towards the length now, the viscous force between the two adjacent layers, when it is moving in upward directions, it reduces gradually. So on moving this length of the plate now, the particle velocity is gains, that layer velocity is gains, and after reaching at a certain distance, that is the height of delta, it gains a maximum velocity, that is the velocity of the fluid which is having at the initial stage now. So this layer, that is the layer at which it attains that maximum velocity or the initial velocity of the fluid, it is called boundary dynamic layer, and this height is called here now boundary layer thickness. So generally it is represented by delta now. This retardation process here now, the velocity is becoming 0 when the fluid layer is touches the stationary plate because of viscous forces present in it now. So the layer which is adjacent to it and above it, the resistance forces comparatively it decreases. It attains from 0 velocity to certain velocity. On moving in upward directions, the viscous force present between the layers it decreases. It attains maximum velocity, that is its initial velocity at a distance of assume delta height from the surface of the plate. This thickness is called boundary layer thickness. Here, if you take the ratio of the velocity of the layer to the initial velocity ux, if it is equal to approximately 0.99, that is nothing but equal to 1 now. That means the layer velocity which is equal to the initial velocity with which it is touch the stationary plate, then that layer, that thickness is called here now boundary layer thickness. That means at which it is attaining the initial velocity of the fluid. Generally it is represented by delta now. The velocity of profile in the boundary layer depicts the variation of velocity with respect to the y. Y is nothing but representing that is the height of the boundary layer with respect to the plate surface. Here when the y increases, the velocity also increases. At a distance of y is equal to delta x, it is having the velocity of the fluid which is having at initially now. That is before touching the plate now. So the flow consists of here two regions now. First one is here, this region at which the velocity is almost it is equal to 0, that is coming stationary, and becoming here higher values now. That is when it is moving from the here intersection point 2 toward the left side, that is the velocity is gaining. At this moment, the velocity gradient is maximum. At the same time, the shear stress is also maximum. On moving towards, that is the right side of the fluid, the velocity of the layer is gradually increases now. So the velocity gradient as well as the presence of stresses that will become minimum now. So this is also called your potential flow. This figure is called. The boundary layer thickness increases along the direction of the flow over the plate as the effects of viscous forces drive now. The application of velocity boundary layer is used for determination of shear stress. Then the dimensionless coefficient, it is called coefficient of viscosity, which is the most important to determine the viscous forces or the shear forces which are present in the fluid. So here the net shear over the plate in a flow wall, shear stress and shear stress behind the boundary layer is here 0. Here at this moment the shear stress is maximum, and on moving this towards this is nothing but towards the left side, somewhere it is having, that is the maximum velocity is attained such that the ratio of fluid velocity, that is the layer velocity, to the initial velocity, if it is equal to approximately 0.99 or equal to 1 now, that means at this moment the shear stress present at this layer is equal to 0. But it is having maximum values when it is touching the surface of the plate now. So at the surface of the plate, that is at y is equal to 0, that means at this position now, the shear stress present is determined by using the relations. So tau s is equal to mu into dou u by dou y. It is equal to now at y is equal to 0 now. So from this tau s is representing the viscous stresses, or sometimes it is also called shear stresses now, which is equal to mu is representing the dynamic viscosity of the fluid, and du by dy it is representing velocity gradient. So the velocity gradient can be determined if the functional relationship such as u is equal to fy is available now. Because where u is representing the velocity at a distance of y, that is the velocity u is representing the function of y. If it is available, we can determine the velocity at any point y from the surface of the plate now. The continuity and the Newton laws of motions to the fluid, the coefficient of friction can be defined as Cf is equal to tau s divided by rho u air alpha square divided by 2 now. Rho u square divided by 2. By using this relationship, we can determine the coefficient of friction which is the present here between the plate as well as the boundary, that is layer of the fluid. In heat transfer, the friction coefficient is by analogy is want to provide a value of a certain number. Okay, based on hydrodynamic boundary layer, here problem number 1, the air at 20 degrees centigrade flow for both sides of a surface measuring 0.2 into 0.2 meters. This is known as the cross section of the plate now. The drag force was 0.075 newtons. Determine the velocity gradient at the surface. The kinematic viscosity as a value of 15.206 into 10 to the power of minus 6 meter square per second. The density is equal to 1.205 kg per meter cube. Also determine the friction coefficient if the free stream velocity as the value of 40 meter per second. Here using the relations tau s is equal to, that is the friction, that is the shear stress is given by mu into du by dy now, where mu is representing the dynamic coefficient of friction, dynamic viscosity, but dynamic viscosity is equal to it is a product of kinematic viscosity multiplied by the density. Hence, this above equations, that is if it is the equation number A, it can be represented as here tau s is represented shear stress, hence force is equal to shear force is equal to stress multiplied by the area, hence force is equal to, it can be written as the product of shear stress multiplied by the area, which is equal to mu into A into dou U by dou Y. But here now already we discussed where mu is the representing dynamic viscosity. It is a product of kinematic viscosity as well as the density of the fluid. So just substituting mu is equal to mu into V now. This equation, since the force is acting, the drag force is on both sides of the plate, hence one side is nothing but equal to half of the drag force, which is equal to 0.075 divided by 2. It is equal to already given this value is equal to 15.06 multiplied by 10 to the power of minus 6 meters square per second. So it is given here area, here mu is equal to, here mu is equal to 15.06 to 10 to the power of minus 6 multiplied by the area, that is the kinematic viscosity multiplied by the here now the density, which is equal to here now 0.02 mu into A, it is given. So here 1.2025 it is given now. This is known as the density into dou U by dou Y now. So from this relationship we got to here it is known as kinematic viscosity, just multiplied by the area multiplied by the density is given into dou U by dou Y at Y is equal to 0 now. On solving these equations, that is the velocity gradient at Y is equal to 0, that means near the plate is equal to 51,660.6 meter per second per meter. The friction coefficient is obtained by using the relations Cf is equal to tau s divided by rho u alpha square divided by 2. From this relation we got to tau s is equal to, that is the friction stress is equal to 0.075 divided by 2 because it is both sides divided by 0.2 into 0.2 it is given into 2 by it is given 1.205 into 40 divided by 40, which is equal to 0.973 into 10 to the power of minus 3 to the coefficient to the dimensionless number. So here we are taking concept of thermal boundary layer. It is just comparing with the previous one, that is a hydro boundary layer. Here is also the plate is kept here only, it's stationary. But in previous case, because of presence of viscous forces, that is the velocity of the layer which is touching the stationary plate, that is almost becoming 0, and the layer velocity gradually increases when it is moving in upward direction, so when it is moving just over the plate now. At certain height we have taken delta at which it is attaining this maximum velocity, that is the initial velocity of the fluid now. That thickness is called a boundary layer thickness. Here this figure is nothing but comparing with the, that is thermal boundary layer, it is comparing with the hydro boundary layer. But in this case the plate is kept at a certain temperature, as in the temperature of the plate is here represented as a Ts now, and the fluid temperature is represented as a T alpha now. Here when just the layer of the fluid, when it touches the stationary plate, the heat transfer is taking place from the hot surface of the plate to the liquid surface by using only the conduction process. This after that, from one layer of the fluid to another layer, that convection process is taking place now. So the particle internal heat of the next layer, just by using convection process, the velocity gradient is which is developed gradually decreases now. So that means here the velocity of the gradient, just when it is touching the stationary plate, it is given by here now. Tau s is representing the temperature of the plate now, and tau alpha is representing the initial temperature of the fluid now. This is known as the here now temperature gradient divided by here the distance we are taking. But at this moment the temperature difference is maximum at initial stage. But when it is moving in upward directions now, Since the convection heat transfer is taking place from one layer to another layer, since already it is a temperature raises, the temperature gradient is decreases when it is moving at a distance of delta x from its surfaces. So at a certain point, the temperature difference between the layer and the layer, which is almost equal to the temperature of the fluid which is having initially before intersecting the plate now. So here the distance y at which the ratio of Ts minus T now, that is Ts is referent temperature of the surface of the plate, temperature at the surface of the plate. Here T is representing the temperature at a distance of y from the plate. The difference is here, it is called temperature gradient, divided by Ts minus T alpha. T is a different temperature of the plate, and T alpha is representing the temperature of the fluid initially before touching the surface. If it is equal to 0.9 and approximately 1, this is called here, this height is called boundary layer thickness, that is here represented by now. The flow is again similar to the in previous region. It consists of two regions. One is a thin layer at which it is having maximum temperature gradient, and after that the temperature gradient is decreasing, and finally it is becoming zero when it reaches a height of delta, that is a boundary layer thickness. Okay, these are the two layers. One is having just maximum temperature gradient, one more is the temperature gradient is becoming here negligible now. So here the temperature distribution is taking place. The first at the near the when the cold fluid is touching the hot surface of the plate, the temperature, that is heat energy, flows from the surface of the plate to the fluid by using conduction process, which is given by Q is equal to minus of K dt by dy now. At y is equal to 0. Y is nothing but representing the distance of the layer of the fluid with respect to the surface of the plate. It is nothing but at the intersection we are taking, that means the y is equal to 0 now. Here the heat is transferring by using only conduction process, where K is representing thermal conductivity of the materials, dt is representing the temperature distance at a distance of dy now. That is dt by dy, this is called gradient here at y is equal to 0 now. So by using this equation 2, we can determine the magnitude of heat energy that flows from the plate to the liquid layer. This after that, the heat energy is transferring one layer to the another layer by using convection process, which is given by here H is equal to, that is Q is equal to H into here A into here T minus here we are taking the layer distance between is equal to Ts minus T alpha now. Here from these two relations, just we are having since it is a steady state conditions now, that is the amount of heat energy that is flowing, it remains constant. So equating just 1 and 2, we got to here H is equal to, that is H into, since the surface area is also constant, and so we can take the H into Ts minus T alpha. So from this relationship we got to, that is H is equal to minus of K dt by dy divided by, that is at y is equal to 0, divided by here Ts minus T alpha. So from this relationship we can determine the convective heat transfer coefficient, which is most useful to determine the temperature distributions this over the plate of having thickness of delta, that is the boundary layer thickness. Okay, based on this boundary layer thickness, we are having here problems. The air at 20 degrees centigrade flows over the plate at 60 degrees centigrade. The temperature at location 0.5 mm from the surface is measured as 40 degree centigrade. Determine the value of local convective heat transfer coefficient. The thermal conductivity may be taken as 0.2656 watts per meter per degree Kelvin. So in this problem, so the given data is the temperature of the air, that means before touching the surface of the hot fluid, is given 20 degree centigrade. Generally, it is represented as T alpha now. That is the temperature, atmospheric temperature or initial temperature now. The temperature of the plate is equal to, is given Ts is equal to 60 degrees. Your temperature at a distance of 0.5 mm, that is y is equal to 0.5 mm, it is equal to 40 degrees. Here it can be taken as T is equal to 40 degree centigrade now. The thermal conductivity is equal to 0.2656 watts per meter per degree Kelvin. So the temperature gradient is equal to dt by dy is equal to, we can take it as here the temperature of the surface is equal to 60 degrees. The temperature of the fluid is given 40 degrees. Hence the temperature gradient is equal to dt by dy is equal to minus of 20 divided by 0.005 now. Because here now the thickness is given 0.5 mm. Here it can be always represented in meters. That is 0.5 divided by 1000, that is meters, which is equal to 0.0005 meters. So from this relationship we can determine the temperature gradient. So in equation number 1, in order to determine convective heat transfer coefficient local, it is equal to H is equal to minus K. According to the previous equation we have taken minus K. Minus K means here the temperature gradient is negative, hence it is treated as minus value. K is equal to the thermal conductivity of the materials, which is equal to 0.2656 watts per meter per degree Kelvin taken. Here dt by dy at y is equal to 0. That is, it is given now minus of 20 divided by 0.005 divided by here Ts minus T alpha, where Ts is representing the temperature of the plate or the surface. Here 20 degrees represents the temperature of the fluid just before touching the hot plate. So from this relationship we got to it equal to 26.56 watts per meter square per degree Kelvin. That is, as the distance is small, the linear variation of the temperature is assumed, but earlier it is in the form of curve now. Here, third problem, air at 20 degree centigrade flows over the surface at 80 degree centigrade. That is, according to this problem, T alpha is equal to 20 degree centigrade. Over the surface, that is Ts is equal to 80 degree centigrade. The local heat flow was measured at a point as 100 watts per meter square. That is Q by air it is equal to, that is the amount of heat transfer per unit area. It is given now, which is equal to 1000 watts per meter square is given. See, estimate the value of local convective heat transfer, that is H is equal to how much we have to determine at the surface and the temperature at a distance of 0.5 mm from the surface. That is y is equal to here 0.5 mm, which is equal to 0.5 divided by 1000, that is converting into meters, which is equal to 0.005 meters. The thermal conductivity of air can be taken as 0.02826 watts per meter per degree Kelvin. Okay, now once again I am taking the temperature of air is equal to T alpha is equal to 20 degree centigrade. Surface temperature Ts is equal to 80 degree centigrade. Temperature at a distance of 0.5 mm, that is y is equal to 0.5 and T is equal to 400 degree centigrade. This is given. Thermal conductivity K is equal to 0.02656 now. Q by A is equal to 1000 watts per meter square. So from the relations now, we are having Q is equal to H into AS divided by multiplied by Ts minus Tf. This is nothing but the amount of heat energy that is flowing by using convection process, where H is equal to coefficient of convective heat coefficient. So from this relationship we got to Q by AS, because here it is given 1000 per meter is given, meter square. And so from this relationship Q by AS is equal to 1000. So 1000 H into here Ts minus Tf, that is 80 minus 20 degrees. 80 is representing the temperature of the plate, that is surface. 20 degrees the initial temperature of the A now. So the amount of heat energy that is flowing in the liquid is given by this equation, which is equal to, by using this equation we got H is equal to 16.67 watts per meter square per degree Kelvin. But using these equations now, Q is equal to, we are having here 1000, it is equal to K into dt by dy, where dt by dy is representing the temperature gradient at y is equal to 0. From this relationship we got to dt by dy at y is equal to 0 is equal to minus half 35,385.7 degree per meter now. So the temperature at 0.0005 meters is equal to, it is given 80 minus here 0.005 into, it is given temperature difference gradient is given 35,385.7. From this relationship we got to the temperature at a distance of 0.005 meters is equal to 62.3 degree centigrade. So the temperature, fourth problem, the temperature ratio, that is the Ts minus T divided by Ts minus T alpha. This is called here now temperature ratio. It is equal to by divided by 0.0075 in a flow over the plate. If K is equal to 0.03 watts per meter per degree Kelvin, determine the value of convective heat transfer coefficient. Here we are taking one figure now. This is nothing but representing just X when the fluid is flowing now. Here at this position it is going like this. At this position the temperature gradient is maximum. Here the heat energy is transfer taking place by using conduction process. The temperature gradient is equal to Ts minus T alpha, where Ts is representing the temperature of the plate, T alpha is representing temperature of the fluid. Since the gradient is more, maximum energy that is transfer is taking place at the surface of the plate. Here at a distance of here y, the temperature is the T means the ratio of Ts minus T alpha divided by Ts minus T alpha, Ts minus T divided by Ts minus T alpha. This ratio is equal to, it is always the function of distance only, that is the boundary layer thickness, which is given y divided by 0.0075 is given. Just by using the relations, we have to determine the value of convective heat transfer coefficient. So the relations between, when we are considering the flow of heat by using conduction as well as the convection process, since it is a steady state condition, the amount of heat energy flowing by conduction process is equal to the convection process. So by equating those two equations we got to H is equal to minus of K into dt by dy at y is equal to 0. Y is equal to 0 nothing but at the initial position now, that is when the fluid is having contact with the earth surface, only conduction process is taking place. That's why we are taking it is equal to y is equal to 0 divided by Ts minus T alpha. So by using the relations now, Ts minus T divided by Ts minus T alpha is equal to function of equal to y divided by 0.075 is given. From this relation, so here Ts minus T is representing, that is the temperature gradient. Here this equation it is there. When we differentiation these equations with respect to the T, so it is equal to Ts is a constant, hence it is equal to minus of dt by dy. Here it is also constant is there now, Ts minus T alpha, which is equal to by integration is equal to 1 divided by 0.00759 now. That is equating, just differentiating this equation with respect to the y now. So from this relation, so dy by dy is equal to, we got to, from this relations, Ts minus T alpha divided by 0.00759 now. So this is the equation number 3 now. So from the equations 1 and 2, we got the H is equal to 0.03, that is the K value is given, into Ts minus T alpha, because it is known as Ts minus T alpha is equal to temperature gradient, which is equal to Ts minus T alpha divided by 0.0075. It is given, that is K into dt by dy at y is equal to 0 divided by Ts minus T alpha. These both are equal, same magnitude now. The remaining values is equal to 0.03 divided by 0.0075, which is equal to 4 watts per meter square now. This is known as the convective coefficient for heat transfer. Here problem number 5. The temperature ratio Ts minus T divided by Ts minus T alpha is equal to sine of pi y divided by 0.015 in flow over the flat plate. If K is equal to 0.03 watts per meter per degree Kelvin, determine the value of convective heat transfer coefficient. So by using these equations, which is obtained because we are taking first the heat energy is flowing from the surface of the plate to the fluid which is flowing over it. At the starting it is having condension, so afterwards the convection process is taking place. So at y is equal to 0, that means this is called y now. That is the boundary layer y. But y is equal to 0 means here at this position now only conduction process is taking place. That is the amount of heat energy that is flowing. It can be represented as K into per unit area, or K into, if take area K, it can be treated as Ts minus T alpha now. So Ts is representing the temperature of the hot surface, T alpha is representing temperature of the fluid now. Afterwards, the heat energy is transferring by using convection process, and moreover it is steady state conditions. That means the amount of heat energy is flowing, it remains constant. It can be written as that is Q is equal to minus of here now H into A into here Ts minus here T we are taking. T is nothing but the temperature at a given position now. That is at y is equal to, we are taking T now. That is equating this equation number 1 and 2, we got H is equal to minus of dt by dy at y is equal to 0 divided by Ts minus T alpha. So here now by using this equation we got to Ts minus T alpha divided by, sorry, here Ts minus T equal to Ts minus T alpha is equal to sine of pi y divided by 0.015. And doing just a partial differentiation, the above equation with respect to the y, in order to determine the temperature gradient. Here the variable Ts is representing the temperature of the plate, it is a constant now. T alpha is representing temperature of the fluid which is touching the hot plate, it is also constant. Hence, and differentiating with respect to T, we got to dt by dy, because here minus we are taking, into Ts minus T alpha, here Ts minus T alpha, which is equal to, here on other side direction, sine pi y, here sine pi divided by 0.015, the differentiation of so and so. That is the differentiating with respect to y on both sides of the equation. It is a 1 and 1 more like this. And doing we got to since it is a constant now, the remaining value is minus of dt by dy divided by Ts minus T alpha. It is equal to sine in differentiation of sine of pi y divided by 0.015 is equal to cos pi y divided by 0.015 into the constant, it is the differential constant of this one now. That is a pi y is differentiation 1 is there, hence it can be written as a pi divided by 0.015. So minus of dt by dy is equal to, from this equation, so we got to pi divided by 0.015 into cos into pi by 0.015 into this denominator values goes upward direction, so we can take it as Ts minus T alpha. It is also coefficient for this coefficient factor for this values now. From this relation we got to at y is equal to 0, that means I am substituting these equations now, because we required temperature gradient at a distance of y, that is near the plate, it is equal to y is equal to 0. That means in this equation, we are putting y is equal to 0, that means at this position. So pi divided by 0.015, it is there already. Cos here, this entire value is equal to cos 0. Cos 0 is equal to here 1 into Ts minus T alpha. So by using this relation, we got to pi by 0.015 into Ts minus T alpha. From equations 2 and 3 and comparing, we got to H is equal to 0.03 into minus of pi by 0.015 into Ts minus T alpha divided by Ts minus T alpha. Both are get cancelled. The remaining values is equal to 6.28. Okay, these are some of the problems we have taken in order to explain the thermal boundary layer. And for collecting that materials, just followed the given here shown the book, textbooks as well as the reference books which are shown in this slide now. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.